In this video, we're going to go through buffers. We're going to answer the essential question, how do buffers maintain a stable pH when small amounts of acid or base are added into the system? So a buffer is a solution that resists changes in pH when small amounts of acid or base are added. So it's going to contain both a weak acid and its conjugate base. Those are there to neutralize whatever's being added. So we can add either an acid or a base, and we're going to have either the weak acid or its conjugate there to neutralize what's being added. So it contains a conjugate pair of a weak acid and its conjugate base. So this is the format for a buffer system. Notice we have our acid, we have our conjugate, and it is a reversible reaction, meaning it can go both directions. So if we rewrite to solve for Ka, it would follow the normal format that we have used in the past. And we can also rewrite Ka to solve for H+, like if we were trying to find its pH, by rearranging the equation, and we would end up with this. So we'll come back to that. All right, so when we add OH, we're adding a base. So again, notice our reaction is reversible. It can go both directions. So if we add a base, it's going to combine with our acid, and it's going to neutralize that base. Our acid is going to go down by whatever the concentration of our base was. Our conjugate base is going to go up. So our pH is going to increase slightly, but not by very much, because our ratio here isn't going to change by very much. Okay, so our pH increases slightly, but the ratio ratio HA to A doesn't change much. Okay, so the pH is going to increase slightly, but again, not by very much. That's the purpose of a buffer system. All right. Now, when we add an acid, notice our reversible reaction is going to go the other direction. So when we add an acid, it's going to react with the conjugate base. Our acid is going to get neutralized. Our conjugate base is going to go down because it's being neutralized. And our acid on the other side of the reaction is going to go up. Our weak acid will go back up. So here, the pH is going to decrease slightly, but not by much, and slightly, and it's because the ratio of HA to A minus, stays relatively the same, more or less. Okay, so let's look at an example here. This is going to look like a lot. So it says, how many grams of sodium acetate are needed to make 50 milliliters of a buffer with pH 4.55 using 0.1 molar acetic acid, and it gives us the Ka for acetic acid. Okay. So first thing that we're going to need to do is we are going to need to find H+ from our pH. Okay, so we're going to find H+. And this is relatively easy because we're just going to take our pH and we're going to reverse it. So if our pH is 4.55, we can find H+ by just doing base 10. So it's going to be 10, and then our base, our exponent is going to be the pH, which is going to be 4.55. Okay. So if I plug that into my calculator, I get 2.82 times 10, and it is to the -5th molar. Okay, so that's our concentration of H+. Okay, now that we have H+, we are going to use our rearranged Ka expression. So we're going to take Ka, we're going to rearrange it. It's asking us to find basically the grams of our conjugate. So we need to find the concentration of our conjugate. So we're going to rearrange this equation. And in doing so, we get the concentration of C2, H3, O2, minus, because we've lost that hydrogen, is going to be equal to Ka times, so our acid's going to go on the top, so this is going to be HC2, H3, O2, and then in our denominator is going to be H plus, and we've got concentrations here. Okay, so we've rearranged our equation to find our conjugate. Now it's just a matter of plugging everything into our equation to find things. So we know H plus, and we know, let's see, we know that our acetic acid, it's 0.1 molar. This is our acetic acid right here. And we know Ka. So it's just a matter of plugging everything into the equation now. So Ka is 1.8 times 10 to the negative 5. And our acetic acid is 0.1 molar. H plus we found previously. So that is just going to be 2.82 times 10 to the negative 5 molar. Okay, if I plug this into my calculator, I get 0.0639 molar. Okay, so great, we've got molarity, but that's not what the question's asking for. It's asking for how many grams. So remember, molarity is moles over liters. In order to get grams, we're going to need to find our moles. So I'm going to take my molarity and multiply it by the volume. So my molarity is, let's see, we just found that. So it's going to be 0.0639. And we're going to multiply that by the volume. We want to make 50 milliliters. So we need to convert that to liters, 0.05 liters. Okay, so here, if I multiply this would be 0.003195 moles. And then I just need to turn that into grams. No problem. So we're going to take those moles and we'll multiply it by the molar mass, which is 82.04 grams per mole. And we end up with 0.26 grams. Wow, that was a lot of work just to find our grams. Okay, so last thing we're going to look at really quick is to choose an indicator whose pKa is close to the buffer's pH. So in the last example we were looking at, our pH was 4.55. So looking at the buffers, we want to find one that is close to that. So no, maybe, no, no, no. So bromophenol blue is going to be our closest to the pH of our buffer system. And that's it. Those are buffers.